Welcome to the Cosmic Savannah with Francois Campher
and Jacinta Hayes. Each episode, we'll be giving you a behind-the-scenes look at world-class astronomy and astrophysics happening under African skies.
Let us introduce you to the people involved, the technology we use, the exciting work we do, and the fascinating discoveries we make.
Sit back and relax as we take you on a safari through the skies.
All right. Hi, Jacinta.
Hi, Francois.
How are you?
I'm good. Just the two of us in the studio today.
Quite an empty studio today. Quite nice to be back in the studio, considering that we were in the pendulum room before. It's nice to have room to sit.
Yes, for anyone who has not been following the Cosmic Savannah, this season has been utter chaos. Yeah. This is actually the last episode of Season 6.
Yes, indeed. We're ending Season 6 here because it's the end of year and we are done.
We are tired. We are very tired. And Dan and Siamiso would usually be sitting here in the studio with us, but they are at a conference and traveling, and who really knows where they are in the world at the moment. And Francois and I are sitting as far apart from each other as we can because Francois is sick, has a cold, and I don't want to catch it.
Fair enough. Yeah.
Thank you for your consideration, Francois.
No problem. All right. So today in the studio, we actually have our first live interview guest, which is Professor David Buckley, who will be speaking to us about the Southern African Large Telescope, which has recently celebrated its 20th birthday.
Yes. We usually do this at the end, but let's do it now. How are you? How's your year been?
Long. Yeah, it's my first year of masters, which is quite a different pace to honors because you don't have the classes, you don't have that rigid, normal university structure of lectures and assignments and then exams. You've just got a research project, which is quite weird. And the project that I chose is slightly out of my comfort zone. So I had a lot of reading papers this year, trying to figure out what the hell I'm doing. And it still feels like I haven't actually done very much, right? It continuously feels like I should have done more in a year, given that I have nothing else going on really except this. But yeah, it's been an interesting year actually. Got a lot of news. First time I've ever traveled to Europe for work as well.
You've had a lot of firsts this year.
Yeah, went to Hamburg to present at the Black Gem and Meerlicht science meeting. Got to actually first time ever observe the real telescope, the 1.9 meter at Sutherland. So yeah, it's been an exciting year, but it's been long.
Yeah.
And you, Jacinta, how are you?
I'm good. I'm tired. It's definitely that deep fatigue that comes at the end of the year. Really definitely ready to wind down. Finished my teaching semester.
Great.
How finished marking all the exams. It was okay. Yeah, it was okay. It's just my third and a half year of running this course. So I'm third year galactic and extragalactic astrophysics. I feel like it should be getting easier, but it's somehow getting harder as I'm trying to put more and more and more into the course. Being an academic is hectic. If anyone's thinking about it, it's amazing. It's great. It's so hard.
Yeah.
It's so much work, but definitely what you were talking about, Francois, is very normal in terms of all of a sudden your only deadline is in 2 years. Submit a thesis. You're like, okay. And for ADHD people like us, that is torture.
Yeah.
That is impossible to try and get anything done with. But I think you'll be surprised that you've actually done a lot more work this year than you think you have. And what actually have I been up to? Well, this year I went to Australia for a research visit with one of my master's students, and then I went to Germany to the SAAO conference to see.
Oh, that was big. That was a big conference.
in Görlitz, and to see kind of the whole SAAO community, to see it's this obviously big radio telescope being built, half in Southern Africa, half in Australia, and it's under construction right now, and to hear the updates and to start the science planning for the surveys that we're going to do with it, to be sad about how delayed SKA Mid in South Africa is by 2 years. So we're still looking at 2029 for it to start, its testing phases. But it's closer than 10 years. So that's exciting.
Yeah, that doesn't sound too bad.
Yeah. But all in all, it's been been a pretty good year. The Cosmic Savannah, I mean, we do our best.
We've tried.
We know we are so inconsistent.
Yeah.
We apologize, but we do have to fit this in around our insane schedules. So hopefully you guys have enjoyed at least some of the content we've been producing. But yeah, we definitely we'll end the season here, and we'll hopefully start again next year with season 7.
Yeah.
Pending funding. Watch this space. Feel free to donate if you want to.
Any sponsors are welcome to email us at.
But anyway, speaking of large telescopes, I think that's a pretty good segue for our...
Excellent.
Thank you. For our guest today. So why don't we hear from our guest, David Buckley?
Yeah, let's get David. In the studio with us now is Professor David Buckley. Welcome, David.
Welcome,
Thank you.
David.
Thanks, Francois. Thanks, Jacinta. Nice to be here. Yeah.
You are our very first guest live in the One Button studio.
I'm honoured.
So thank you for agreeing to be not only on the podcast, but also on video.
Not at all. Yeah.
So, Dave, tell our listeners just briefly who you are, where you're from, what you do.
Sure, yeah. So I'm an astronomer. I'm originally from New Zealand, and I studied in Australia, but then I came to South Africa in 1988 as a postdoc at UCT here. But then I moved to the South African Astronomical Observatory. And then in 1999, I was appointed as project scientist for the SALT project. So for the 6 years of construction of that, I was part of the project team that, basically designed and built SALT.
Sure.
And I have an important question, if you don't mind, Francois, before we get into this.
Please do.
How is your tortoise, Tabitha?
As manic as ever, Jacinta.
I had the privilege of meeting Tabitha once, and I have never seen a tortoise that loves being scratched under its chin. And when you do, she goes, ah!
Yes.
Did you know that tortoises make that sound?
We didn't know that when we inherited her, and we were worried that there was something wrong. So the previous owners who'd left her to us because they were emigrating said, no, that's what she does all the time. It's just she enjoys that, and that's her vocalization. Yeah.
And you tried to re-naturalize her to
Well,
environment.
we were thinking of it, but she thought she was a human, really, so she was beyond that. Yeah. But she's all like, we got a permit for her and everything, because, you're not allowed to keep tortoises without having a permit. So it's all above board. Yeah.
So
that's good.
You can attempt to segue with that, Francois.
Yeah, I don't think I can. Not been in this business long enough. But David, we're here to talk to you about SALT, and I see you're wearing a very apt T-shirt as well today. Yeah. I wish I had some SALT merch actually, but we'll talk about that later. Can you briefly give us a description of SALT, just for our listeners who are unsure of what SALT actually is? Yeah.
So it's the largest telescope in the Southern Hemisphere, largest optical infrared telescope in the Southern Hemisphere. So it's effectively a 10-meter telescope, which, if you look at the moment, there's only like 4 others apart from SALT. So there's, and they're all in the Northern Hemisphere. So there's the one the Spanish have, they're called Grantacan on the Canary Islands. There's the 2 Keck telescopes in Hawaii, and the Hobby-Eberle telescope, which is sort of the cousin of SALT. In McDonald Observatory. And these are telescopes that have huge light collecting area. And because of the fact that they want to build them to that sort of size, 10 meters, you can't build a single mirror like that size. So they're made up of, in the case of SALT, 91 individual segments, hexagonal segments that sort of slot together and are sort of controlled independently to effectively become a 10-meter single mirror.
Okay, that's very interesting. So SALT, as you say, it's a 10-meter class telescope. So that means the diameter of the telescope is 10 meters across.
Exactly, yes.
That is huge.
It is, yeah.
That is very big. And you say that...
And the collecting area, the amount of light or information, if you like, that gets collected is proportional to the diameter squared.
Sure.
So compared to, say, a 1-meter telescope, this would be 100 times... the collecting area of a 1-meter telescope.
Wow, that's incredible.
So I heard a rumor that the mirror has been cracked once before by a hammer being dropped on it. Is that true?
No, I don't know that. I tell you what has happened. That could be true. That no one's told me. They've kept me in the dark about it. But what did happen once was there was an accident when we were exchanging segments, because we have spare ones and we have to recoat them because they have a reflective metallic coating. So typically we recoat them once a year, all of the segments once. So there's a continuous operation of taking them in and out, cleaning them and recoating. And on one occasion, the lifting mechanism failed and the mirror segment was about a meter from the ground and it just dropped onto the concrete floor and then toppled over and smashed into 1,000 pieces.
Ooh,
so
that's
fortunately,
worse.
that was the end of our second spare. I'm glad we got 2 spares, but we only have 1 now. But that's the only really catastrophic thing that I'm aware of.
Maybe that's the story I'm thinking of.
Yeah.
So do you mean that the mirror is made up of different segments?
Yes, yeah. So the telescope is made up of all of these hexagonal segments that are sitting in the telescope in what's called a support truss. But each mirror is controllable, so we can move it, tip and tilt it, so that we can sort of align them to the degree of accuracy that you need to be able to get good image quality that is, better than, say, what you would get just from the natural image quality through the atmosphere. Yeah.
Okay, that's very interesting. So I want this episode to be kind of taking us back to the beginnings of SALT as an idea, to paper, to construction, to instrument.
Yeah.
Because I've only ever known it as instrument, because I'm too young to have remembered it being constructed. So in 1991, you joined SAAO after your postdoc.
That's right. Yeah.
Yes. And in this point in time, I believe, SALT was actually not meant to be a 10-meter class telescope.
You're dead right.
It was supposed to be a 3.5-meter
Yep.
NTT telescope.
Exactly. Yeah.
Can you tell me a little bit about that idea first? Like, where did the idea come from that South Africa suddenly needed this big telescope here?
It came from the fact that, about that time, the end of the 80s, 90s, it was sort of realized that our biggest telescope was only a 1.9 meter. And so just in terms of competition, competitiveness with other observatories around the world, we were starting to lag behind. We only had a 2-meter class telescope, but most other places had 4-meter class telescopes. So the director of the observatory at the time, Michael Feast, had sort of realized that this was something that needed to be addressed. And they started motivating for 4-meter class. And about the time I joined the observatory, Michael Feast was like wanting me to become involved in this project that at that point was only like 3 people involved in it. So it was like the director, him, Ian Glass, who's a now retired astronomer from the SAAO, myself. And we worked with some engineering companies in Cape Town, consulting engineering companies, to put together a proposal for this 3.5 meter. So that involved visiting particularly ISO, who designed and built the NTT in Chile.
So ISO is the European Southern Observatory,
which is I would say the major observatory in the world. It's the one where the very large telescope, 4 8-meter telescopes are in Chile. They're building right now something called the extremely large telescope that'll be 28 meters in diameter.
It's ridiculous.
So,
insane, actually.
No, 38, I think. Anyway, it's big. But at that point, the idea was that there was particular interest from the Max Planck Institute at the time. So the previous director, El Sasa, was quite keen on a 3.5 meter telescope, particularly in Namibia, which is where Max Planck owned an small observatory already on top of a mountain called the Gamsberg Mountain, which is sort of southwest of Windhoek it's close to the Hess Gamma Ray telescope site. And so the idea came together that the Max Planck Institute would fund the construction of the telescope. South Africa would provide the operations of the telescope, and Namibia would contribute to some of the infrastructure that's needed, like roads and power and all of that. But by 97, or even earlier, it started to become clear that this wasn't going to work, primarily because the Max Planck Institute were not so keen, other than the outgoing director, on this idea, and they were far more interested in a sort of joint project with people in the US and Europe called the Large Binocular Telescope, which was basically two 8-meter telescopes. So that's what happened. Basically, the support in Max Planck was sort of withdrawn, and also there was worries about how would South Africa operate an observatory in another country. All of that sort of political. So it sort of died in '97, but that was coincident at the time of the sort of opening of the Hobby Eberly telescope in Texas. And so at that point, we became aware of this other telescope, which, because of its innovation in design, was a lot cheaper. In fact, no more expensive than the original 3.5 meter that was being considered. So that's how that all happened. I mean, there's a lot of other stories, backstories of like how we got approached by that group from the Hobby Eberly telescope. They were basically going around the Southern Hemisphere trying to sell the idea, and it just happened that I was in my old alma mater, Siding Spring Observatory, Mount Stromlo, when they visited and gave a talk on it.
That's in Australia, by the way.
In Australia, yeah, exactly. And so when I heard this talk and I talked to them afterwards, I thought, this is really great. We should get on board with this. So I sent an email to the then director, Bob Stobie, and that's how it all started. We then invited them to come. They came and presented this idea. People were enthusiastic about it. And then the next phase, and when you've got the astronomers on board, the next phase is to get government support. And that's, when we had to sort of convince the NRF and then the Department of Science, Science and Arts and Culture at that time. But that all sort of panned out. Yeah.
Okay, so there's a whole like complicated backstory there. But what were the key challenges that you found in convincing the international institutions to commit to the SALT partnership? Because it's not just a South African or a Southern African thing. It's actually an international telescope.
It is. And when we had basic tacit approval from government that this is something that they would support, that was with the condition that we would have matching funding. So 50% of the telescope funding would come from outside of South Africa. So at that point was when we started to make contacts with a lot of institutions, universities around the world. And it sort of started off with the idea that we would have a meeting in Cape Town that was held at the waterfront called Science with Salt. And that happened in 96, I think, February 1996. So that brought together some of the institutions who had expressed an interest in coming on board on that project. So some institutions in the US, Poland were interested at that time. And so that meeting had both scientists and it also had engineers, because we had parallel sessions where there were the people who built the Hobby Eberly telescope in Texas. So some of the contractors who were involved in that came, and we had the project manager for HET organize the technical aspects and invite local industry in South Africa who we thought might be interested in being part of this. So that's how it all began. And then by about 1999, I think, November or so, we had the situation where we had like 75% commitment of the remaining funding. So the government sort of declared green light on the project, and that's when it really sort of kicked off towards the end of 99.
Wow. Okay, so 99, the project kicks off, you've got your funding, you are appointed as
and
the
also
project
the project
scientist.
manager was appointed
Yes.
around that time, a bit later. So initially the project team, well, it was still had Bob Stobie as the director, was still very strongly involved. We had other people involved, like the HET project people, and we also, again, took on board some of the consulting engineers that we had previously for the 3.5 meter concept, so that we could sort of move it forward before we even had a full project team on board. But after Cobus Mehring and I were appointed, we went through the process of interviewing, all of the different engineers that we would need to bring in to manage the telescope, because it's quite a technical, advanced telescope. So many different engineering disciplines, including optical engineering, which we didn't have any local expertise on that. So we hired a optical engineer from Poland who came on board for the team. And most of the people who were appointed were from the sort of defense-related Denel and other organizations like that, who were involved in things like guided missiles or attack helicopters, highly technical things, which you'd think had no relevance to telescopes, but
turns out they did.
So, yeah.
That's very interesting. Now, as the sort of project scientist, what is your main responsibility as the project scientist of something like a telescope? Yeah,
well, it's basically to define the requirements. So there's a sort of overall scientific requirements of the telescope, like, okay, what fraction of the sky should it cover? How fast should it move from one target to the other? What's the tracking accuracy? What's the image quality? So there's a whole bunch of high-level requirements, and that's for both the telescope, but then also the project scientist had responsibility for defining the first light instruments that would go on it, because a telescope's only as good as the instruments that it feeds. So that wasn't a unilateral decision by me. It was a process where we formed a science working group within the partnership, and we would have, during the meetings several times a year initially, we would start defining what instruments we wanted on the telescope, and ideally finding people within the partnership who would be willing to contribute to the construction of the telescope, of the instruments. There was only limited funding for the instruments, and so some of the what we really wanted to be able to do, it was to have some of the partners doing in-kind contributions where they provided, person power and the actual buying, items for the instruments, which would be offset to, say, operations costs, or they would be considered as if they made a cash contribution to the telescope.
Okay.
So that was like my main responsibility. That requirement document had to be turned into a technical specification, so the high-level technical specification for the whole system. It's a massive document, and it includes in it like all of the things that you do in a project like that, of defining all of the acceptance testing, that you do of individual components, but also the integrated systems as they get put on the telescope. So that was the sort of project scientist's responsibility. So there's always a little tension, between the engineers and the scientists, because the engineers just want to do, what's written down on a piece of paper.
Yeah.
And so we have to make sure that spec is as clear as day. And the big thing to avoid is what they call scope creep, is like after you've defined this, a lot of astronomers will come up, oh, it'd be nice if you could do that or this. I'm not saying there was no scope creep, but we tried to minimize it as much as we can.
Well, that doesn't sound like astronomers. Late to the deadline, ever.
But it did result in quite innovative instruments, and some people would say much too complicated instruments. But nonetheless, we did end up with, I think, quite a compelling and competitive instrument suite on SALT by the time we had first light. Yeah,
so this sounds like, I mean, as an astronomer myself, I don't have any skills in project management like this. How did you?
Neither did I.
Did you
I
just learn on the job?
Instrument. The first thing I did when I joined the observatory was I wanted to get involved in building an instrument. So I built a very simple fiber-fed high-resolution spectrograph, not because I had a scientific interest, but because it
sounds
Which
simple,
is basic, just simple.
it was like a capability that we didn't have, but people wanted, but no one else was willing to sort of step forward and say, all right, I'll do it. I was sort of young at the time, and I thought, what the heck, I'd like to experience that. So that was my only background. But yeah, I guess I've always had a sort of interest in engineering and things like that, and working with these guys who are trained engineers in many different disciplines, structural engineering, mechanical engineering, precision control stuff, and then learning the whole systems engineering approach that I'd never heard of before, which is like really the heart of all big technical projects, particularly in sort of defense force related things like a helicopter, for example. So we had a really good systems engineer on the SALT team who's now doing a great job on SKA.
Wow.
He moved off to that after SKA.
Mm-hmm. So the construction years were 2000 to 2005, which is why we're celebrating 20 years of SALT now in 2025.
Yeah.
So it sounds like that must have been a really intense time.
It was.
And I've heard, so I did my internship at Gemini South, which is a big telescope in Chile.
Yeah.
And I learned there that there's this sort of, like you mentioned, a slight tension between the engineers and the astronomers, where the engineers consider it their telescope, and then the damn astronomers mess it up during the night, and the astronomers think that it's their telescope, and they're like, very engineers don't waste our time, we want to use this telescope. Anyway, did you have any memorable moments, good or bad, from the construction years?
Well, a lot of very sort of interesting moments, I would say, that are memorable. We didn't have that degree of tension that you mentioned for Gemini, because at that time the instruments weren't completed before we had first light. So we were moving towards integrating a camera that we would do the image quality testing, which is the key thing, and pointing and tracking tests. So there was this instrument that was built at the SAAO by my colleague Darragh Donoghue, and that was the main instrument that we would test with. And those tests started happening, I think it was even before 2005, when we had a subset of the mirrors, not all of them, all 91. We had 7 when we got the first images, because you can create an image with only 7 segments.
Sure.
So it was like a gradual process, and in that final year, 2005, the final complement of mirrors were in the telescope by May. And then there was an intensive time of doing, commissioning acceptance testing of the telescope up till the November opening. But there were some, occasional things like I remember in particular when the crane lift for a major part of the structure was happening. So they'd assembled this truss and the bottom part of the telescope that holds the mirrors. It's all made out of steel, big I-beams and so on. And it's assembled next to the telescope before the dome was on, and the crane had to lift it up, move it up as high as the ring wall of the telescope, over and down. And as they were doing this first attempted lift, it got about 1 meter from the ground, and these straps on the crane started to unravel, and it unceremoniously dropped back onto the big wooden blocks that it was sitting on. And the face of the project manager went as white as a sheet, because I can say that all of the health and safety things that should have been in place were not. Like
To put it
hard
lightly.
hats
Oh
and
my God.
family members coming to watch this. I mean, none of them were standing under it. We had better,
Good, yeah.
Common sense.
but that was common sense. Yeah.
Oh my
So that
goodness.
was one. That was one thing, and then the other one that springs to mind was when in the sort of hectic time of commissioning. They're working long hours, day and night, and the engineers finished sort of at the end of the night, and they went to bed, and they forgot to close the dome.
Oh,
And
no.
so in the morning, when the sun rose, the telescope is at some point pointing to the sun. And so the sun is then focusing the light, not through any instruments, thank
Yeah,
goodness.
luckily. Yeah,
They would have been
jeez.
burned to
But there was a
smithereens.
cable along the top of the telescope, an electrical cable, and that was, it's like a magnifying glass and
Yes.
from
On
the
an
sun
ant,
on a
yeah.
piece of paper.
You can burn it.
Can you imagine
Yeah.
a 10-meter magnifying glass? but the spot is like this big. Fortunately, it's not a narrow
Okay,
little
luckily.
spot.
Okay, so like the size of a, what would you
Nonetheless.
say this size is?
Yeah, it's about
Jeez, I
10
don't know.
centimeters
Yeah.
or so in size.
Probably,
And that basically cooked a cable. So they were all highly embarrassed about this. And I saved a little bit of that cable, and at the end of year sort of Christmas party presented it as a sort of mounted as a sort of prize for the most foolish thing that maybe happened that year.
Like the wooden spoon prize, but it's the
wooden
burned
spoon prize,
cable
exactly,
prize.
Exactly. So no names I'm not going to say, but they know who they are. Yeah.
Well, I hope they took it. They took it well.
Yeah.
That's hilarious. So it takes all of this construction time, right? Finally, after all of these, despite all of these issues, it gets turned on. When was first light for SALT?
I should know this. It was. I think it was in 2004. Look, I'm really sorry. I should have remembered my dates.
So
first light was with a subset of mirrors, right?
yeah,
But we called it engineering first light.
okay.
So
there's,
proper,
Okay, we want astronomy first.
Yeah.
Yeah, like
Wait,
when
first
the-
of all,
astronomy first
The
light.
big mirror gets
Yeah.
turned on
Yeah,
for the
yeah,
first
that's
time.
sorry. First of all,
I
what
think
does
it was about August 2005 was
Okay.
proper first
Okay.
light with all of the segments.
so? What does first light mean exactly?
First light means like, okay, you have the completed telescope, which as far as, as you've been able to ascertain from all of the tests that you've done, maybe even acceptance tests in the factory for some items, but acceptance tests on integrated systems on the telescope. You've got to the stage where, okay, you're really going to use this in anger, in the sense that you're going to look at a real object as if you're really observing, well, you are.
Yeah.
So that's first light, when you first sort of have
Collect
the
your
whole
first light.
end-to-end of photons hitting the mirror, being focused up to the detector, and you see the resulting image.
Okay.
That was first light. So the first light images, because usually first light is a big publicity thing.
Yeah.
You remember probably the first light images of JWST were
And
astounding.
and
Rubin
Vera C.
Observatory.
Rubin, yeah.
So we did a sort of small scale version of that, nowhere near as spectacular, but nonetheless, we had color images that we created from observations of different filters of like well-known objects, globular clusters, galaxies, star-forming regions, and so on. And it showed that and dense stellar fields that showed it all looked fine. Image quality looked good. That's a second story, that it wasn't as good as, it wasn't as stable. Yeah.
Yeah.
So we then had some problems in the commissioning period that we had to solve with that issue. Yeah.
Okay.
And so, what has SALT been used for science over the last 20 or so years?
Yeah. I mean, everything under the sun, really. I mean,
Above the sun, further than the sun.
well, not even further than the sun, because some near-Earth asteroids
That's
have
true.
been
Yes.
observed, right?
Yeah.
So it's been used for solar system astronomy, and mostly driven by some of our overseas partners, particularly Poland, actually. So both near-Earth objects, but also these icy bodies in the outskirts, trans-Neptunian objects and things like that. But that's a sort of very small fraction of what it's been used for. Mostly it's been used for, I would say, half and half for like studying the Milky Way, the stellar content of the Milky Way, so individual stars or star systems or clusters, but also a large amount of extragalactic astronomy, so looking at other galaxies. And that was where there was originally very little sort of activity in South Africa in the time of the 1.9 meter. There was very little extragalactic astronomy being done, a little bit, but you need the aperture for that. You need a light gathering power of a 10-meter telescope.
Yeah.
So that was a whole new area that has expanded enormously. SALT also has the capability of multi-object spectroscopy, so it doesn't just look at one object at a time necessarily. It can look at several. So that was a new something for us because that's never been done before. But, to answer your question, it's an evolving thing. I mean, astronomy is an evolving science, as you know. And so the things that we designed the telescope to do back in 1999, in many respects, we ended up doing other things that at the time we didn't even, dream about because they hadn't been discovered. It's like, for example, the Keck telescopes, the two first 10-meter telescopes in the world, their science case was completely different to where they made a name for themselves, like, for example, finding the black hole in the center of our Milky Way. That was never on their science case, but they did it.
Got a Nobel Prize.
Yeah, and so it's a similar thing with SALT, that there's many things that have come along that we didn't talk about. I mean, one of the big projects I'm involved in is following up transient objects, which are things that suddenly come into existence, in terms of suddenly there was nothing before. Yeah. And we really never sort of said, oh, well, SALT's going to do a lot of work in transients, but now it's like one of the largest programs on SALT. And so I think you can go through most fields of astronomy and say that SALT has been been used for virtually everything, except say maybe the most demanding, faintest objects in the universe, little pin pricks of light that's
JWST's job.
It's too
Space telescopes.
Yeah.
So can I ask another science question? So I'm going to forget the name of this. Is it called ARSCO or
ARSCO.
ARSCO. So Francois was telling me about this the other day.
Yes, right. The white dwarf pulsar.
Yes. So that's what you're working on at the moment, isn't it?
That's one of my own passions. These now there's 4 discovered.
Okay. Yeah. So can you tell our audience just a little? I know we're running out of time a little bit. However, it's so cool. I've only just learned that you can get a white dwarf pulsar. Now, for anyone who doesn't know, a pulsar is usually a rotating neutron star. So the corpse of a dead giant massive star that has gone supernova, ended up with a neutron star made purely of neutrons, intense magnetic fields, can be rotating and letting out this like radio pulse, which you can use for timing very accurately and a lot of different things. But recently I've learnt that you can get a white dwarf pulsar, where a white dwarf is the kind of the corpse of a smaller mass star, which has not gone supernova. It's just kind of gone planetary nebula and let out its outer layers, and you end up with this like carbon core just left, which we call a white dwarf. How is that pulsing? What is this?
Yeah, well, the thing about it is, the reason neutron stars pulse and create pulsars is they have an intense magnetic field, as you mentioned, and that magnetic field generates a huge electric field, which then strips off charged particles that stream out from the surface of the neutron star, and it loses energy. And the pulses of the rotating neutron star, which is really fast, I mean, it can be fractions of a second, like the Crab Nebula pulsar, they slow down because of dipole radiation. So you measure over time, you measure a change in period. In 2016, a colleague of mine in the UK, Tom Marsh, had followed up a star that amateurs had been looking at that had been misclassified as a fairly dull pulsating star back in the 70s. And what they discovered was it showed a very strong pulsation at about 2 minutes. And it wasn't just in the optical where they were looking. It was across the whole electromagnetic wavelength region. So the first radio observations were done by ATCA in Australia.
We call it the ATCA.
The
Australia Telescope Compact Array.
The Compact Array. So they were the very first radio observations. And in the Nature paper that Tom wrote, it had these pulsations right across from radio, infrared, optical, UV, Hubble Space Telescope observations. Observations that myself and colleagues did here, we did polarization, and we are amazed to see that the polarization goes up and down by 0 to 40% over the same spin period, just like you see in the crab pulsar. So that's when the term white dwarf pulsar was sort of came up. In the discovery paper, Tom had tried to put it in the title, but the editor said, no, they don't like that. But by the time we'd written our polarization paper, we put it in the title and they accepted it. Because apart from the fact that it's not a neutron star, which is a defining characteristic of a pulsar, really, everything else about it, the fact that it has, electrons in a strong magnetic field traveling near the speed of light, so they emit what's called synchrotron radiation. That's what causes the pulsations across the whole electromagnetic spectrum, from the radio right through even to X-rays, actually. So it's a weird object, and it's the strange thing was that it's sort of in our backyard. It's only 116 parsecs away in a giant molecular cloud in Scorpio. And, it was known as a variable since the 1800s from photographic plates. Yeah. But no one knew because they didn't have the time resolution to see the fast pulses.
Cool.
So that's a sort of new area of interest, because it could be in a funny sort of state in binary evolution, a sort of short-lived transition state, which we've discovered, as I say now, at least 4 of these systems. And we did it's bright enough that we could use the smaller telescopes at Sutherland, but we also use SALT to do what's called spectropolarimetry, which is looking at the polarization as a fraction of wavelength. So that's something which has become a sort of passion of mine in my own research, apart from the transient work as well.
Cool.
All right. Then last question, David. So SALT has now been operational for about 20 years. And I suppose I want to know from your perspective, what has the impact been of SALT on the South African astronomy community?
Yeah, I think it's been huge. I mean, when SALT came along, even before we got approval, there was a little bit of skepticism on part of, sort of established astronomers that we could even do this. We'd never built a telescope before.
Yeah, and famously, SALT has a lot of South African engineering people building it, right?
And
it's mostly South African components.
No, exactly. And so I think it was the success of SALT, and there's no denying it, the success of SALT led to the whole success of the SKA bid, that we could show the world that we could take on a highly technical project. I mean, it's like orders of magnitude less in cost. It was a really cheap telescope to build, excuse me, something like 18 million US dollars, which was back, that's really cheap. But anyway, compared to what the SKA is.
We don't need to talk about it.
But it's a lot more, around $1 billion euros,
something
right?
like that. Yeah.
But anyway, that showed that we do have the technical capability. But right from the get-go, when SALT started, there was this realization that we need to grow the community of astronomers. And so there was this outreach program, the SALT Collateral Benefits Plan, which I remember, a number of us traveled around South Africa to all the universities to talk about this project and to encourage students who might be studying physics or had an interest in astronomy to consider doing astronomy. And at that time, about the same time, actually, the National Astrophysics and Space Science program started, which brought students from all over the country to train them up in astronomy at a sort of fourth year level honours and then masters. And so all of that has led to now a whole cohort of young early career astronomers who have done their PhDs, some of them using SALT data, and now have become, staff members at this university or moved overseas and have successful careers in astronomy overseas. And the nice thing about the science that we've been doing with SALT is that there's been a lot of student involvement in it. So, for example, on the program that I run on the SALT transients, we had no one really looking at novae. These are exploding white dwarfs in binaries. And so a student who was doing his PhD at UCT basically took this on board and led the whole NOVA follow-up. And he ended up getting a Hubble fellowship, moving to the US, and now he's a professor in Texas,
Wow.
And one of the world experts on novae. So all because he had this wonderful access to SALT, getting data, and many other observatories around the world, both space-based and ground-based.
Cool. What's his name?
Elias Adi.
Oh, very cool.
Yeah, he did his PhD here. I met him actually when he was finished his master's he's from Lebanon.
Wow.
So we had a meeting in Lebanon in, I think it was 2016 or 17. And I remember seeing his poster, and he was telling me about the work that he was doing on open clusters. And one of my colleagues, Shazreen Mohammed, who used to work at the observatory, took him on as a PhD student, and he's blossomed ever since.
So you knew him way back when.
Yeah.
All right.
Cool. Well, thank you so
much, David.
Not at
for
all.
joining us.
It's been great talking to you about the whole project, and the next phase is going to be more challenging in some respects because construction's done and so on, but what are we going to do for developing it in the future? Because that now sort of needs a step up in sort of funding for new instruments, because you can't just sit with what you have to develop all the time.
Yeah.
So what do you think that future looks like?
Well, I think it's encouraging in that all of the partners in SALT are really committed to it, and I think the government's committed to it as well. It's just really in this current environment of okay, we need a certain amount of money to do this, and finding that money can be challenging, but not impossible. Yeah.
Well, thank you very much, David.
Okay, great.
Well, that was a fascinating look back on the whole history, because I just came to South Africa. As you know, I'm from Australia, and I'm just I don't know anything about South African astronomy. I know there's they've got the biggest optical telescope in the Southern Hemisphere, but I don't know what else. I mean, everyone knows about SALT in Sutherland here in South Africa, right? But I don't know. To me, I'm just never thought about the fact that it hasn't always been there.
Yeah.
What was the history of it being built, and the politics and the money, and
No, it's interesting to hear as well, because I just know SALT because as a kid in grade 5, they talked about, we've got SALT, it's the best thing in the world. It's got the, big optical telescope in South Africa. South African astronomy is real. And I visited SALT as a kid, actually.
Cool.
I remember them telling us all about the segmented mirrors and the way that it turns on a cushion of air. And I thought this is space tech. And the coolest thing was that they said, and that I still remember it, that the guy who gave us the tour was actually an astronomer who happened to be awake that day and took us around and showed us the telescope. And I remember him saying that most of these components were actually made here. I think the only thing that he mentioned that was particularly not made in South Africa were the mirrors, but the rest, most of it was constructed by South African companies.
Cool.
Which was weird. I mean, as a kid, you didn't think South Africa had this capability. So yeah, I've just grown up with SALT. So it was interesting to hear how it goes from idea, paper to project to construction to telescope. And especially hearing the impact that it has had on South African astronomy, especially, and it continues to have, was my favorite bit. That was by far the most interesting for me.
Oh, that's cool. Did it play a role in you deciding to become an astronomer?
Sort of, yeah. I mean, it was quite weird when I went to observe this year in Sutherland, because I remember that trip that we did when I was very, very young. No one told me when I was like 11 going up to see Sutherland that, you know, future you will be driving up here with a rented car from the astronomers hostel to come and observe up here with, okay, not with Salt, with a 1.9 meter. Yeah. Although I did go and steal Salt's coffee one night.
That's the trick, isn't it?
Yeah, well, that's the best coffee in Sutherland, actually. Yeah.
Okay, I have one thing, and I should have said this to Dave, but I happen to know that he's behind the cameras there and he can still hear us. I think they've missed a trick. Why can't we purchase salt shakers? Like, we need to, and there needs to be a telescope called Pepper. In Sutherland, right?
I've said the salt shaker thing before. We could 3D print them.
Yeah, we need salt and pepper shakers.
Jacinta, salt and logos. Cosmic Savannah merch. We can have a merch store. And we can
this is how we're going to fund next season. All right, you heard it here first, folks.
Pepper would be hard. That's a hard acronym to come up with, though. Like
Pepper.
Something polarimetry.
Yeah.
I don't know.
But I think we need an instrument for salt that's called Peppers. And then we can have salt and pepper shakers.
That would be funny.
All right, I think we've... It's probably time to end the season
here,
I think.
So I think. Yeah, so this is the end of season 6, because we are tired and it's the end of year.
It has run over 2 years.
Yeah.
But we got to the end of it somehow.
Yeah.
So thank you for your patience with us, and thank you for sticking with us. And we hope you enjoyed this season and that you'll join us again for the next season of the Cosmic Savannah. Yeah, you can visit us still on our website, thecosmicsavannah.com, where we'll have the transcripts, links, pictures, and other stuff that was related to today's episode. You can follow us on X, Facebook, and Instagram at Cosmic Savannah. And now apparently also on TikTok, but I don't know anything about that, so you'll have to ask our interns, the youths. The youths, yeah. That's Savannah spelled Savannah. You can also watch the podcast now on YouTube, mostly. Yeah, mostly. This episode at least you can, with closed captions, which can be auto-translated into many different languages, including Afrikaans, isiXhosa, and isiZulu. A special thanks to Prof. David Buckley for speaking with us today. Also, thanks to our audio editor, Nick Rushton, our podcast manager, me, our social media manager, Sumari Hatting, our assistant manager, Kaashifa Saloojee, and our awesome intern, Sisa Shibane. Thanks also to Mark Olnut for music production, Susie Karras for graphic design, and Brian Mashamola and Michal Werchek for photography. We gratefully acknowledge support from the South African National Research Foundation, the Square Kilometre Array Observatory, the South African Agency for Science and Technology Advancement, the South African Astronomical Observatory, the University of Cape Town Astronomy Department, and the One Button Studio here at UCT. You can subscribe on Apple Podcasts, Spotify, YouTube, or wherever you get your podcasts, and we'd really appreciate it if you could rate and review us and recommend us to a friend. And we'll speak to you next time on The Cosmic Savannah.